You ready to start?
Yes.
Okay, I will allow you to share your screen.
Okay.
So you can start.
Okay. Can you see my screen?
Yes, yes, I can see it.
Uh, Karen, we're not hearing you.
Yes.
All right. So, with all the incredible developments of science and technology, the medical field had its share from it. One of the biggest evolutions that happened in the recent years was the development of implantable medical devices, or IMDs, which helped in diagnosing and curing millions of health cases. Jawad and I will be discussing some of the powering methods of these implantable medical devices. In this presentation, we will be presenting the options that are now studied to power implantable medical devices. We will be focusing on the three main groups, studying for each the most relevant examples. The first category concerns IMDs that run on single-use batteries, like the power from the human body to generate mechanical and electrical energies. And finally, the third category concerns harvesting energy from the environment to charge IMDs. And for each of the three mentioned categories, we will be talking about its purpose, its mode of functioning, the advantages and limitations. During the past decades, the quality and efficiency of the healthcare system have exponentially grown as a result of the advancements in electronics and wireless technologies. This development merged with innovative biomaterials has allowed for the invention of miniaturized and biologically compatible sensors that could be inserted in both humans and animals, permitting the diagnosis of very challenging body parts as well as cell parts. Implantable medical devices, or IMDs, are inserted in the human body and they consistently follow up on the status of a patient and accordingly enforce homeostatic adjustments. They are useful to replace a missing biological structure or to support a damaged biological structure or even to enhance an existing biological structure. And many of these devices require a power source. So, the first mode of powering is through the use of batteries. A battery is a transducer that converts chemical energy into electrical energy. It contains a anode, which is the source from which electrons flow out, a cathode, which is the sink where electrons accumulate, and an electrolyte separating the two. It is desired for the one-time use batteries used by the IMDs to have a prolonged lifetime to avoid having to put the patient under surgery every few years to have the batteries replaced. The first type of battery is the lithium iodine batteries. Lithium has the highest tendency to lose electrons. It has only one electron in its outer shell and always wants to lose this electron. Here is a schematic of a lithium ion battery. At the cathode, there is a lithium metal oxide. At the anode, there is a graphite, and an electrolyte separates the two. In green are the lithium ions, and in blue are the electrons on the outer shell, which they want to consistently lose it. And we will next see what the role of each component is. So, when we connect a power source across the arrangement, the positive side of the power source will attract the electrons of the outer shell of the lithium atoms in the metal oxide. These electrons will flow through the external circuit as they cannot flow through the electrolyte because the electrolyte only permits the ions to pass through it. And so they will go through the external circuit and reach the graphite layer on the right-hand side. In the meantime, the positively charged lithium ions, they are now positively charged because they just lost an electron. They will be attracted towards the negative terminal and they will flow through the electrolyte. So now, Next slide, please, Jawad. Okay. The lithium ions and electrons are both in the graphite side, on the right-hand side. They are detached from the metal oxide, which is on the left side, and they are detached from one another. And the battery is fully charged. This is the unstable state. Why is it unstable state? Because the ions were separated from their electron on the outer shell. So now we want to connect a load. After connecting a load, the lithium ions want to go back to their stable state as a part of the metal oxide. And to do so, next slide, please, Jawad. They will go through the same route as before. The lithium ions will go through the electrolyte to get back to the metal oxide, and the electrons will take the external circuit, and by taking this circuit, they will be passing through the load, which is the IMD, the implantable medical device, and powering it. So what are the advantages and disadvantages? The first advantage is that the lithium iodine battery is very light, which is desirable because we are placing it inside the human body. It has a higher energy density than most rechargeable batteries, which means that it gives a lot of current, having less surface. And its rate of charge loss is less, which permits it to give a current range in the microampere. And this is desirable for the IMDs because many devices operate on this range, for example, the pacemaker. And it has a prolonged lifetime because it gives current in the small range. So it lasts longer. Disadvantages involves risk of bursting sometimes. It is costly. And its complete discharge damages the battery. This is why we said it's one-time use battery. So when it has discharged completely, we need to replace it. And it is sensitive to very high temperatures. The second battery of interest is nuclear batteries. Some materials have radioactive properties. These radioactive elements release energy as either kinetic energy or as generated heat. In either case, the energy released can be used to generate electricity. For this presentation, we will be discussing the first case only, that is to generate electricity from the heat released from a radioactive element. So how does this happen? A material containing unstable nuclei is considered radioactive. Radioactive decay is the process by which a non-stable atomic nucleus loses energy by radiation. And we have seen in our course that energy losses by radiation is nothing but heat released, which will be used in what we call a Seebeck effect. In the Seebeck effect, there is a generation of electrical potential due to the application of a heat source, and we will next see how. The Seebeck effect is a phenomenon in which a temperature difference between two dissimilar electrical conductors produces a voltage difference between the two. Meaning, consider two semiconductors, N-type and P-type. The charge carriers in an N-type conductor are electrons, they are charged negatively. And the charge carriers in a P-type conductor are positive, they are holes, they are charged positively. When heat is applied, heated charge carriers inside the two conductors, they will flow toward the cooler one. This distribution of charges builds an electric field across the junction. And when a conductor is used to connect the two ends of the junction, charges begin to flow through it. And this is how we produce an electric current. Also, this battery is very lightweighted. It has the highest energy among all other batteries, and some of them can reach hundreds of years because we are talking about radioactive elements. Their decay, their half-life can reach hundreds of years. Disadvantages, of course, rely on it having a risk of being confronted to radiation. It's our human body after all. It is very costly because the elements can be very rare and sensitive to any changes in temperature because this is how it works, depending on the temperature. Um, so the main goal for researchers now is to reduce or even to halt the times when they need to cut open the patient to have the batteries of his IMD replaced. One major promising field resides in the human body, which is rich in chemical, thermal, and mechanical energies. To make the idea clearer, think of the activity of breathing, which generates 0.8 watts, or even the heat of the body capable of generating up to 4.5 watts, or the arm motion generating energy that can reach 60 watts. And to understand these values, think of your cell phone, which needs 1 watt to last up to 5 hours. So naturally, the human body faces temperature differences from one place to another, resulting in a temperature gradient. And we have seen earlier, a temperature gradient can create a potential difference following the Seebeck effect explained earlier. And please stop me if you want me to re-explain this mechanism. All right, next slide, please, Rawad. So medically, the use of a thermoelectric generator involves putting one surface of the device in direct contact with the skin of the patient, and the other surface is left in contact with the outside ambient temperature. When heat flows by the junctions, an electrical potential arises as a result of the Seebeck effect, and the voltage is generated having the following magnitude: N times S times delta T. N is nothing but the number of thermocouples. A thermocouple is nothing but the connection between the N type and the P type. Delta V is the change in voltage, generated voltage across the semiconductors. S is a coefficient known as the Seebeck coefficient, and delta T is the temperature gradient between the skin, usually, and the ambient temperature. We are talking about power taken from the motion of the human body. So of course it is endless, an endless power source. It doesn't require any recharging. It is always operating. It is very environmentally friendly and doesn't put the patient under surgery every few years for battery replacement. The limitations are that the temperature gradient inside the human body doesn't exceed 8 Kelvin, which is not capable of generating much electricity or not more than few microwatts. And of course, some IMDs already require not more than a few microwatts, so it is good. And it is, for now, it is still only used on the outer skin. It has never been used inside the skin. Why? Because of size limitations. A piezoelectric material Piezoelectric materials are ideal for monitoring and diagnosing bodily signals because, on one hand, they work by converting mechanical energy to electrical signals, and on the other hand, the body is subjected to great mechanical loads every day. Piezoelectric materials that are capable of conducting electricity can occur in nature, but they can also be man-made. Among many, some of these materials consist of cane sugar, topaz, bone, and mostly quartz. What is similar among these materials is that they all have an asymmetric crystal structure, which gives them the property of conducting an electric current. In fact, crystal materials contain the same number of negative and positive charge, but they are dispersed randomly, and thus they do not allow the flow of a current. So, when a certain load is applied to such materials, this load, this compressive force or tensile force, disrupts the charges, or simply we can say it causes them to realign themselves. And when they are realigned, they permit the flow of the current. And of course, the higher the load, the more reorientation of the charges happen, and the better the current is.
Okay, so the third way to use your body to create energy is using electrostatics. Electrostatics is the study of charges at rest. It has always been around, but was seen as some mysterious and mystic occurrence a long time ago. Electrostatic induction is defined as a redistribution of charges in an object caused by the electric field of a nearby charge. In the recent years, this technology became more and more popular to power IMD. Notably using an electrostatic generator, which was used by exploiting either the ventricular motion or the heartbeat to power cardiac pacemakers. The electrical system exploits the motion and vibration from the human body combined to an electrostatic energy harvester to power the device. By moving and changing the distance between the charged plates of a capacitor, we are creating a movement of electrons and therefore creating electricity. Choices made in the mode of charging of the harvester and the actuation of the capacitor will have effect on the fabrication process, capacitance, charging speed, cost, and output energy. We should also notice that this system can be micromanaged, micro-machined, which means that it is easily implementable with IMDs. Now, to solve the problem faced with single-use batteries and IMDs powered by the human body, a third possibility was proposed: external power transferring mechanism. The use of external energy source can solve issues like battery life, low energy output, and potential poisoning, while providing other benefits like an easy communication between the IMDs and smart devices. Those devices can be powered optically, mechanically, or electromagnetically. Optical charging is the process of using photovoltaic cells to transform the energy from light sources to create electricity that could be used to power devices or charge batteries. In the biomedical field, the PV cells were used for many purposes, which include powering implementable medical devices. It is important to know that photovoltaic cells are made of multiple layers, and notably two semiconductors, which we can see in the previous slides on the left. The first layer is a semiconductor positively charged called p-type, and the other one is a negatively charged n-type. This difference in charge allows electron movement and therefore voltage creation. Between the two semiconductors, we can see an NP junction, which is dope material that will prevent the scattering of charges. By installing a photovoltaic cell in the implant and using a near-infrared laser diode as an external light source to power the cell, we are able to charge the IMDs. This is possible because depending on the wavelength, radiation access deep in the skin and biological tissues to power the IMD. It has a lot of pros like a great charging speed and amplitude. That's what the transfer which we talked about, and easy and good manufacturing and implementation. The limitations are that it's a new technology, so there is still a lot of trials and errors that should be made. And also, it may be dangerous for the skin until we find a way to prevent that. It can burn the skin due to the laser. And it's still, because it's a new technology, costly, big, and impractical. The ultrasonic transducers are another way to produce electricity. They are using ultrasonic waves to power IMDs. Ultrasonic transducers are machines that are used to create or receive energy and transform it into electricity. By installing an ultrasonic receiver in the implant and using a transmitter as an external ultrasound source, you are able to charge the IMDs. Similarly to light, depending on the wavelength, ultrasound may access deep in the skin and biological tissue to power the IMD. We have two main types for the receiver: the capacitive ultrasonic transducer that uses a capacitor, and the piezoelectric ultrasonic transducer that uses a piezoelectronic sensor. On the left, we can see the capacitor ultrasonic transducer, and on the right, we can see the piezoelectric. In the case of the CUT, so the capacitive ultrasonic transducer, the ultrasonic waves are transformed into electricity through the capacitor. When the waves hit the receiver, they cause the membrane to vibrate. This will change the distance between the two plates of the capacitor, creating electricity in the process. This is similar to electrostatic energy that we saw earlier. In the case of the piezoelectronic ultrasonic transducer, or PUT, the ultrasonic waves are transformed into electricity through the piezoelectric material. When the waves hit the receiver, they cause a change in the form and the size of piezoelectric material, creating electricity in the process. This is also similar to the piezoelectric charging that we saw earlier in the presentation. A third way is to use inductive coupling. So electromagnetic induction is the creation of an electromotive force through an electrical conductor by a varying magnetic field that goes through the conductor. This phenomenon can be used to power many devices, including IMDs. The technology created to power implementable medical device through electromagnetic induction uses two coils, and is called inductive coupling charging. The first coil is connected to the implant and works as the receiver, while the other coil is used as transmitter and is located outside the body. During the charging process, a varying magnetic field goes through the transmitter, through the body, and to the receiver. Electricity will be created and will go through the circuit to be stored in the harvester circuit, which is directly connected to the IMD. All in all, we can say that great improvement and big steps were made in IMD powering during the last years. The recent advances in technology offered us a lot of different possibilities and opened the door to multiple options that are offered to doctor engineers depending on the case they need to treat. Nonetheless, the work is far from being done. There exist no perfect solutions, like shown previously. Also, of the discussed alternatives still have issues to deal with. Single-use battery may be toxic, are not environmentally friendly, and can be expensive. Power generated from the human body may have some issue providing the necessary power, and are still very new, which means a lot of work still needs to be done on critical body parts and the possibility of unexpected side effects. Finally, environmental energy harvesting, even though it provides great upside like data transferring, it is also very new and can have side effects on the skin, notably. In the future, solution will be provided, more studies will be made, and an environmental economical battery that can keep up with all the constraints that IMDs offer will be made. This goal may actually be reached by mixing two complementary options that already exist. Thank you. Here are some of the references that we used to write both our paper and our presentation.
Okay, thank you. So first, I want to welcome Manar. Manar is a PhD student in AUB, and now she is taking a course in teaching. So we will start with her if she wants to ask any questions.
Hello. Yes, please.
Hi, Manar.
Thank you, Dr. Karim. Hi.
Hello.
So any questions, Manar, for Jawad and Karen?
No, I just wanted to make sure that I got things correctly. So you were introducing the different types of the batteries, right? And their applications. And
Yes.
finally, you ended up with like a summary for their advantages and disadvantages, right?
Exactly.
Exactly.
So, okay. Thank you. It was very useful and summative. So thank you so much.
Thank you.
Thank you.
Welcome.
Okay. So first, Karen, can you go, please? If you can, in general, put the number of slides because this will help into the questions. So can you go back, please, to the beginning so that I tell you which slide I have it
Yes.
on?
Yes. Tell me. I guess tell me to stop when I reach the slide.
Okay. Yes. Tell me. I will tell you when to stop.
Okay.
Continue, Jawad.
Somewhere with this.
Jawad, here, can you please give more details about nuclear batteries?
Also about nuclear batteries, yes. Do you want me to talk more about the Seebeck effect or in general nuclear batteries?
Both.
Okay, so nuclear batteries is something that is already used in multiple fields outside of IMDs. They're trying to use it because, like Karen said, we have multiple products that have long half-life. So in nuclear, we talk a lot about half-life. They have long half-life, which means that we don't have to change the batteries multiple times. Now, one problem that we have is that the process can be unstable. and that you can produce heat, which is what we're looking for, but it can, like Karen said earlier, that it can generate too much heat and be dangerous. Our goal is to, while using nuclear batteries, to make the process more stable, while still having the advantages that we have. Now, going back to the Seebeck effect, which is like the heat source, it's also kind of how the PV cells work, in the meaning that by heating, so we also saw experiments where they say that if you heat the PV panels, you can also change the way they receive electricity and generate electricity. So here is the same, because here we are heating the plates, we are actually creating a movement of electrons, because the charges are moving away from the heat.
Okay, thank you,
Going from
Jawad.
the
Thank you.
hot side to the cold side.
Okay. So can you go please down with the slides?
Yes.
Okay, yes, can you stop here, please?
Here,
Before.
Well-
No, not here. No, not here, before.
Okay, piezoelectricity.
Yes. So, Karen, can you please talk about piezoelectricity?
Yes, of course. So piezoelectric material, I'm going to call it a crystal. They have the same number of positive and negative charge. So they are neutral always. The thing about them is that a crystal has them, and the dipoles in a crystal, they are not aligned. They are randomly dispersed, as we can see in the picture, the one on the right. So when we have such randomly dispersed dipoles, current cannot pass through. Imagine this same object, if you want to pull it or compress it, think of it as we are pulling it. It's easier to imagine. This will cause these arrows, the dipoles, to become more vertical, more oriented and realigned. The more we have realignment, the more the current can pass. This is the property of a piezoelectric material. Hello?
Hello, doctor?
Yes, I am hearing you. Thank you. Yes, thank you. I will open a new meeting to start the class. Okay?
Okay.
Okay.
Thank you
Are we
for the
done?
presentation. Yes,
Thank
we are
you.
done. Welcome.